Welcome to today's lecture. Myself, Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College, Ghaziabad. The subject that I am covering in this lecture series is microprocessor KCS 403. The topic that today I am covering is interfacing devices. This is very important topic because whenever we are going to use any microprocessor, so we are not going to use it all alone. We have to use certain input-output ports, or we have to interface this device with the input-output devices, certain peripherals. Can be a LED or the LCD or the keypad or the any keypad matrix it can be. So we have to come across various interfacing devices, and also we can also interface the microprocessor with the memory, in fact. So we have to study about the interfacing devices, that how can the peripheral devices and the memory be interfaced with our processor. So this is what we are going to talk in this lecture. So when we talk about the logic devices for interfacing, so first of all, we will talk about the tri-state devices: buffer, bidirectional buffer, decoder, encoder, and D flip-flop, that is, it can be latched and as well as the clocked. So let's see at these through these devices one by one. When we talk about the tri-state logic devices, by tri-state we mean the device is having the three states. First is the logic 0, second the logic 1, and third is the high impedance state. That you call Z state also. A tri-state logic device has an extra input line called the enable. So what will this line do? That if this line is enabled, this line is activated, then only the device will perform the required operation, otherwise not. So we can see through this device that there are certain inputs and output. There is certain VCC and ground. So whenever there is the connection from the input and output, and whenever the enabled pin is activated, then only the device will perform. So how? This is the truth table. This is the device. This is the input data. This is the output line. This is enable. So whenever this device is enabled, that is the enable pin is activated, then only it will give the output according to the input. So we can see through this at this truth table that whenever the enable pin is 1, then only the output is equal to input. Yes, otherwise this is in the high impedance state. So this should be 1 or 0. It depends upon this operation. That is, you can have a look at this, that enable pin is active high. So whenever there is 1 at this pin, then this device will work. But in this case, you can see this is active low. This is the bubbled pin. So whenever you will give 0 to this pin, then only it will be activated. So in this case, whenever there is 0 at the enable line, then only the output will be equal to input, or we can say then only the device will work. So this is known as a tri-state buffer because it is doing the job of buffer. That is, it is giving the output equal to input, but according to the enable pin. So when the enabled pin is activated, then only the device will work, otherwise it will be in high impedance state in both the cases. So this is a case of active high enable pin. This is the case of active low enable pin. So this is all about the tri-state buffer. So they can allow the multiple devices to share a common output wire or bus by having only one tri-state device to drive the wire bus at any one time, while other buffers remain in their high impedance state. How is it possible? Let's see. So there are two lines at the input which are for selecting the buffer. So suppose these are all the buffers. These are the 4 buffers connected to the output. Now, what is this doing? This is the decoder. According to the input combination of buffer select pins, either of the 4 outputs will be selected. So when this is 0, 0, this line will be activated. When this is 0, 1, this line will be activated. When this is 1, 0, this line will be activated. And when this is 1, 1, this line will be activated. So in such cases, what is happening? When this line is activated, this is the enable pin for this buffer. It means this buffer will be activated and it will give the output according to the input. When this line is activated, it means that it is going to this enable pin of second buffer. So this buffer will be activated and will give the output equal to the input. When this line is activated, that it means it will activate this buffer. It is connected to enable line for this buffer, and this buffer will give the output same equal to the input, and same is the case for this fourth one. So in this way, the multiple buffers can be connected using a decoder, and only one tri-state device is connected to the wire bus. So in this case, this is the wire bus, and at any particular time, only one tri-state buffer is connected to the common data wire or the bus, and others are in the high impedance state. Now we talk about the common buffer, that is the digital buffer. It's a single input device that does not invert or perform any type of logic operation. The buffer is a logic circuit that amplifies the current or the power. It is used primarily to increase the driving capability of the logic circuit, and it is also known as driver. So we all know the purpose of the buffer. It simply passes our input to the output. So in this case, we can see that this is the input, this is output. Here the buffer is connected. Similar is the case with this. So in this chip, there are 6 buffers connected at different pins. This is the ground and this is the VCC. This is the complete chip which is providing the 6 buffers at a time. So when we talk about the buffer, there is no enable. This is the simple buffer and there is no enable pin. Simply it will give the output equal to input. So according to the truth table, no enable pin is there. Simple output is equal to input in both the cases. Now when we talk about the bidirectional buffer, the bus transceivers are tri-state bidirectional devices which allow the flow of data between the 2 points, making them compatible with the bus oriented systems or the bidirectional control of interface circuitry. So in this case, what is happening? That the data transfer is taking place in both the directions. Let's see how. So this is the example that bus transceivers can be inverting, that the TTL 74LS 242 or non-inverting, the TTL 74LS 243 devices. These are the names of the various bidirectional buffer devices. In this, we can see the whole connecting diagram, connecting circuits which are capable of transferring the data in both the directions at a time. So for this, we require the 2 buffers for both the directions. So we will see how it is happening. For a single connection, we can see this is 1 buffer, this is 2 buffer, this is the inverter. Now for one buffer, the enable line is active high. For another buffer, enable line is active low. Why active low? Because this is going through the inverter. So for one buffer, the enable line is active high, and for another buffer, enable line is active low. So this is enable line. This is the input, or it can be output, because the data transfer is taking place in either of the direction. Similarly, this can be output as well as the input. When this is acting as the input, this is acting as output, and when this is acting as output, this is acting as input. So what is happening? Suppose the enable line is 1. So this is being activated. Similarly, this is being activated at a time. So whatever data is being sent here, it will go to this and will transfer to the output. Similarly, whatever data comes here, it goes from there to here at the output. So this point is acting as the input as well as the output at a time. Similarly is the case with this point, and both the buffers are activated simultaneously. When we talk about the decoder, it is basically a combinational type logic circuit that converts the binary code at its input to its equivalent decimal code at its output. So, suppose we are talking about the binary decoders. These are having the 2 bits or the 3 bits or the 4-bit codes depending upon the number of data input lines, and an n-bit decoder has 2 raised to power n output lines. So basically the binary decoders are very popular, and when they are having the n inputs, the number of outputs is equal to 2 raised to power n. So if we receives n inputs, usually grouped as a binary or the Boolean number, it activates one and only one of its 2 raised to power n outputs. Based on that input, will all other outputs deactivated. So the decoder is a commonly used device in interfacing input-output peripherals and memory. So in this way, the decoder is used to connect the multiple outputs to the limited number of inputs. So we can have a look at these examples. Suppose this is 2:4 decoder. Here are 2 inputs and 2 raised to power 2 outputs. Similarly, this is the enabled decoder, which is having the enable line as well. So when this is activated, the 2 inputs gives the 2 raised to power 2, that is the 4 outputs. So this is 2:4 decoder. Similarly, there are 3 inputs, there are 2 raised to power 3, that is the 8 outputs. And this is the enabled, that is the decoder with enable. So in this case, when the enable line is activated, then only this devices will give the outputs according to the decoder. When we talk about the encoder, it is just the opposite of decoder. It's a multi-input combination logic circuit that converts the logic level 1 data at its inputs into an equivalent binary code at its output. So generally, digital encoders produce outputs of 2-bit, 3 bits or 4 bits decodes depending upon the number of lines. So when the number of input lines are 8, so the outputs will be 3. When the number of lines are 4 in any of the input lines are 4 in the decoder, then the output will be equal to 2 lines. So n-bit binary encoder has 2 raised to power n input lines. As I told that this is just the opposite of decoder. So if there are 2 raised to power n, so the outputs will be n. Outputs will be n lines. So the encoder has 2 raised to power n input lines and n bit output lines with common types that includes 2:4, 4:2, 8:3 and 16:4 line configurations. So these are the commonly used configurations in any of the that is the interfacing devices. So we can have a look at this encoder. This is 4:2 encoder. There are 4 inputs and the 2 outputs. So this is the truth table we can see. Suppose the combination is 0, 0, 0, 1. So the output will be 0, 0. When the combination is 0, 0, 1, 0, the output will be 0, 1. So basically what it is doing, it is encoding the binary data into the, that is something coded data into the binary data at the output. So how it is doing that 0, 1, 0, 0. So this will give you 1, 0. So 1, 0, 0, 0. It will give you 1, 1. And this is the don't care condition. So in this way, we can get the binary equivalent data from any coded data at the input. When we talk about the priority encoder, it its output corresponds to the currently active input which has the highest priority. So here it doesn't matter what the lower priority inputs are. It will only test the highest priority input. So the priority varies from D7 having the highest priority to D0 having the lowest priority. So when the input with the higher priority is present, all other inputs with the lower priorities are ignored. So suppose we are considering the second case and this is 1, then also the result will remain same. Whether it is 0 or 1, the result will be same. Similarly, this can be 1, 1, 0 or 1, 0, 0 or it can be 1, 1, 1. It will only test the highest priority input. So if the highest priority input is activated, then according to that, the result will be obtained. So priority encoders are available in standard IC form, that is TTL74LS148 is an 8 to 3 bit and priority encoder which has the 8 high active low inputs and provides a 3-bit code of the highest ranked input at its output. So in this way, the various interfacing devices are used to connect all the peripheral devices or the multiple memories. Finally, there is the D flip-flop. It can be used as the latch or the clock. It can be clocked flip-flop also. So a flip-flop or the latch is a circuit that has 2 stable states and can be used to store the state transformation. So basically flip-flop is what? It is a bistable multi-vibrator. It can be made to change state by changing the signals which are applied to one or more control inputs and will have one or two outputs. So the D flip-flop is widely used. It's also known as a data or the delay flip-flop. So this is the most common used flip-flop whenever we are considering the data transfer. The D flip-flop captures the value of the D input at a definite portion of the clock cycle, such as the rising edge of the clock. That captured value becomes the Q output. At other times, the Q output does not change. So it depends that at what edge of the clock, at what time of the clock, this device is activated. So accordingly, at that particular rising or the falling edge of the clock pulse, that device will give the output according to the input. Otherwise, the previous state does not change. The D flip-flop can be viewed as a memory cell, a zero order hold or a delay line. So this is the general diagram circuit for the D flip-flop. So this is the present state and this is the complementary state, and this is the clock pulse provided through this pin. This is the input. This is set and reset pins. So when suppose the rising edge is 1, then the Q next will be equal to, at the rising edge, the Q next will be equal to 1 and also at the rising edge, the 0 will be equal to 0. So it means that at all the rising edges, the output will be equal to, that is the next state will be equal to the input, and at the non-rising, because it is not working, it is not programmed to work on the non-rising edge. So the next state will be equal to the previous state. So in this way, the D flip-flop works. So that was all about the various, we can say various interfacing logic devices. So the tri-state devices, buffer, bidirectional buffer, decoder, encoder and D flip-flop. All these interfacing devices are used to interface the various peripheral devices or the memory devices to the microprocessor. That's all for the day. Thank you.